Good morning, everybody. Welcome to CS205 again. One notification, homework 3 is due today. I think many of you already submitted it, but if not, just remember to do a pull request, because if not, we won't be able to see it, and then you haven't submitted it. Today, I'm going to talk about transactional memory. And so again, we're in the multi-core world. And there's a software challenge. Well, one can take an application and break it down into many subtasks, many parallel subtasks that each of one of them can run in a single thread, in a different thread, sorry, on a separate core or CPU. But we still need somehow to avoid race conditions. And the question still remains is, how can we write correct, efficient, and scalable algorithms? This is the holy grail of parallel computing. That's what we want, something that would be all of these, correct, efficient, and very scalable. So scalable in terms of both, as we increase the data set, the algorithm will work better, will scale, but also if we increase the number of cores that we have, it will work faster. And so let's take an example. We'll start with this example, and it will follow us through the lecture today. So let's think of a banking system, and we'll just look at a single operation of this banking system, which is called transfer, which transfers X dollars from account I to account J. Well, if I would tell you to do this, you'll probably be doing something like that in your code. You'll read account I, you'll decrease X from it, and you'll store it into account I again, and read account J, increase it by X, and then store it again into account J. This is very simple, and it usually, if you look at how it maps into the CPU or whatever, it usually looks like that. So the compiler does it, basically. So you first read some address in the memory. You store it in a temporary register or local variable, and you just do your operations on this local variable V. You write the output into the memory location that you've got. Again, you read account J, you update the local variable V, and write that value back to account J. This is very simple, I think. There isn't much to see here, but this example will follow us through the lecture. So why is this code a problem when we've got multi-threaded? So let's take, for example, these two bank accounts, account I and account J. Each one of them has $1,000 at the beginning. And we'll issue two concurrent operations. One is called transfer of $200 from account I to account J, and the other is transfer $300 from account I to account J. So let's assume that what happens when we run these two concurrently, what happens is actually the CPUs or the cores actually work as follows. So we first start with the left transfer. So we read account I, so we read it, it says 1,000, and we store it into our local variable V. And then we just update our V and reduce 200, which is the amount that we need to transfer. And so this thread's local variable V is actually 800, okay? And now, let's say for some reason this thread is suspended, the CPU suspends this thread, and lets the other thread, the system lets the other thread run. And so it reads account I, and again, account I, if you read it, it's 1,000. Oh, sorry, yeah, it went out too fast. So when you read it, it's still 1,000, and then we read it into the local variable V, we decrease 300 from it, and then we write the new value, 700, into that place, into account I. And then we continue with the left thread, which basically we write the V value that we had 800 before, write it into account I. We increase account J by 200. So from 1,000, it increased to 1,200. And then we continue with the transfer of the right account, which basically increases it from 1,200 to 1,500. So at the beginning, each one of them had $1,000. So together, it sums up to 2,000. But now, it's basically a larger value. Instead of when you transfer 200 and 300, it still needs the sum still needs to be the same. 2,000, but for now it's like 23,000. And so this is called a race condition, and this is what we want to avoid. So this is basically what we talked about during this class. So there are many synchronization alternatives that we can use. The first one is coarse-grained locks. We'll talk about coarse-grained locks. We've talked about coarse-grained locks. We've talked about fine-grained locks. And in the beginning of the week, I've talked about non-blocking implementations. Today, I'll talk about transactional memory. But just so we all be on the same page, coarse-grained locking is basically taking the entire data set that we have and using a single lock, okay, to lock it. So it's very easy to program, right? If you've got a data structure, you just, before you access it, you acquire a lock, you do your operation. At the end, you just release that lock, and everybody's happy. The problem is that this is basically sequential. Let's say you've got accounts I and J, but you also got accounts X and Y. And you want both of these, all these operations to run in parallel, right? Because these are accessing different accounts. But if you use a coarse-grained lock, you won't get that option. And so another option, we said this is coarse-grained locking. Another option is fine-grained locking, in which each value, each datum that we have in our data structure is basically it has its own lock. And so this is very, very scalable. It's potentially to be very scalable. And you just lock the places that you're accessing, and it's very nice. The problem is that it's usually hard to program. You want to avoid any deadlocks or priority inversion, and it's usually something like a programming convention. So when you lock the accounts, you need to account them by the order of their values or something like that. Yeah. So slow. What is asking whether it's usually slow. So locking. How does locking work? I won't go into details, but I'll just talk briefly. There are different ways to implement locks. These days, most operating systems have libraries that implement locks as follows. You just do an atomic operation, as we saw, like the CAS operation, stuff like that. You just do this operation in order to change a value from, let's say, 0 to 1. And once it's 1, it means that you've got the lock and no one else can use it. When you exit the critical section, you just change that value back to 0. And this is quite fast. It's not something that is very inefficient. The only problem is that they also use other techniques that allow us to have, like, let's say, a queue of waiters. Like, let's say thread A acquires a lock, and now thread B and thread C and thread D also try to acquire that lock. They will be in some kind of queue in order to allow some fair execution. And so this makes it a bit more complicated, and maybe you'll have some more penalty in terms of performance. But it's usually not that high. But again, it depends on your code. If your critical section is very, very short, then yeah, the overhead of using locks is usually higher than what you're going to perform. Then you should avoid that. But if it's pretty long, then you actually don't care. Okay, so this is fine-grained locking, and we've already seen that also in homework too. And the beginning of the week, I talked about non-blocking implementations, lock-free algorithms, for example. And these are very nice algorithms, as we said. They usually use some hardware primitives, such as compare and swap. There's a swap primitive or fetch and add. And it just usually just accesses some of the values that you need and does it in a smart way and avoids many of the lock difficulties and problems. However, when you try to program these kind of data structures or algorithms, it's very, very hard. It's very, very difficult to prove correct, and many people enter some pitfalls when they do that, and we try to avoid that. And so today I'll talk about transactional memory, which is the latest alternative, which began, I guess, around like almost 25 years ago, but gained much traction when people started to talk about multi-cores. So what is a transaction? So a transaction is basically a term that is taken from the database community. The idea of a transaction in the database community is to do a sequence of operations, and then you commit these operations, and all you care about is whether the commit was successful or not. And once it's successful, it ensures that all the operations in that transaction were performed atomically. What does it mean? It means that if someone else looked at that values, you won't see anything that was in the middle. You only see only values before or after the transaction. So this is the idea of a transaction in databases, and the idea of transactions in memory, in transaction memory is almost the same. In transaction memory, it's a sequence of memory reads and writes, so just reading and writing from memory, and it's executed by a single thread, and at the end, the transaction is either committed or aborted. And if the transaction successfully commits, then all its memory operations appear to be executed atomically. Otherwise, if it aborts, then none of its operations, none of its stores actually, just the ones that you write in the memory, none of them take effect. Also, these operations will not be visible usually until the transaction commit successfully, okay? So almost the same. I guess the major difference between transactions in databases and these transactions is the durability. In transactions in databases, if for some reason your database falls, then you've got to have some durability, your server. So meaning that if it falls, it crashes, then everything is stored. If it said that the transaction was successful, it's also stored to disk. And so when it comes back online, you'll still see the values of these operations. Here, however, this is all in memory. And memory, as you probably already know, whenever you turn off the computer, all the memory that it has is basically gone. All the contents of the memory are basically gone. And so it doesn't ensure it, and we don't care about durability in this case. So what are the goals of transactional memory? First of all, it started, and it's still some kind of a goal to have a new multiprocessor architecture in terms of how to handle stuff with memory. And the idea is that they want to implement a non-blocking algorithm, like we saw in the beginning of the week, but they want it to be very efficient. And on the other hand, they want it to be very easy to use, so that every programmer that finishes, I don't know, CS50 or some basic programming course can easily use these mechanisms. And why it would be so efficient? It's basically because it will be either implemented by hardware, or it will be implemented by software mechanisms, sometimes using the operating systems and stuff like, or libraries, which are usually very, very optimized and will be very fast. Okay? So this is the idea. Let's look at still the same example. So we want to transfer from account I to account J. So if we use fine-grained locking, it will probably look something like that. We'll acquire lock Li, then we'll acquire lock Lj, do our operations, and then release them. In transactional memory, the idea is to do something like that. Just take your operations, as you did them before, and just put an atomic block, surround them by an atomic block. And what will the transactional memory underneath it, whether it's software or in hardware, will basically be, will ensure us that these happen in an atomic manner. And I don't think it can get any easier than that, but okay. So this is the idea of transactional memory. If you have questions, again, stop me, yeah. And the first idea of transactional memory was given by Hurley and Moss in 1993. So this is before we had multi-cores, yeah. So their idea was to use this for a multiprocessor architecture where you had many processors, many CPUs on the same board. And they actually proposed something that's called an hardware transactional memory, an HTM, that extends a given cache currency protocol that is basically used in many architectures. So let's just look at an example of why do we need cache coherence and how a simple algorithm that solves it. So the idea is this. We've got different processors on our systems or cores in our systems these days. Each one of them has its own cache. And they all talk to the global memory. So this is nice. And we saw that caches are very, very useful throughout this, this course. But how did they do that? So actually, there's something in between that's called a bus. This is the only thing I'm going to talk about architecture in this lecture. But the idea of a bus is basically a way to communicate between all the processors and the memory and other stuff. But for now, let's just assume that we're just the processors and their cache talk with the memory. So let's assume that processor number 2 issues a read, executes a read of memory location A. Then it first goes to the cache. It sees that it doesn't have that address, and so that value. And so it says there's a cache miss. Once there's a cache miss, this operation goes through the bus to the memory. The memory says, OK, the value is of in memory address A is 10, and passes it also again through the bus to the processor. OK? And just for completeness, this bus is shared between everybody, and everybody can hear all the time what's going on the bus. And so processor number N now wants to read, again, memory location A. It also tries to look at its cache. It sees that it has a miss. And then it issues a request on the bus to the memory. And again, this is passed to that. So far, so good? OK, yeah. We'll talk about it. Yes?
So in this process, what is cache coherence? Just means that when you have a cache miss, you can
Let's look at the, I'll get to that. OK? So now, this is all fine and well. We haven't seen anything new. But let's say that processor N now tries to store a value in location A. And now it wants to store 2. So basically, it will just change in the cache. It can just change in the cache the value to 2. But then the question is, what will happen to processor number 2? Because it sees that it has 10. Well, sorry, yeah, it will change the value to 2 and issue a write order on the bus to the memory. And so the memory will also update A to 2. But what does processor number 2 needs to do in order to have some? The idea of cache coherence is that everybody will see the same values of the memory. Okay? So for that, there is the Snoopy cache coherence protocol, which basically says everything is passed on the bus. So if you just listen, and every time you've got a value, let's say someone says, I've updated location A to something. And if you've got location A in your cache, what you need to do is just invalidate that row. And so when the next time this processor number 2 tries to read A, it will just invoke another it will look at the cache and see that it's not there. And will invoke another cache miss, basically, and get the new value from the memory. So this is the idea of the Snoopy cache coherence protocol. Yeah, it's very simple. It's very nice. It's very useful. Lots of architectures use that. So this is the idea of what a cache coherence problem is and a way to solve it. So far, so good? OK? So what Hurley and Moss said, OK, so let's use the same idea of a bus and the Snoopy cache coherence protocol, and just do this. Instead of just a single cache for each processor, we'll also add something that's called the transactional cache. OK, so each processor will have its regular cache and the transactional cache. Whenever a processor or a CPU tries to, a thread that runs on the CPU tries to execute a transaction, it will just do all its operations on the transactional cache. And we won't allow, and if there's, for some reason, there is this Snoopy protocol that basically invalidates a line in the cache, so it won't only invalidate that line in the cache, it will also say that this transaction should be aborted. Okay? This was their idea. It's a simple idea. There isn't much to it, actually. But they showed, in the paper, if you'll read it, they showed what operations should be supported by the CPUs and how it should actually work with all the fine details that I'm not going to go through. Okay? So this was their idea. So it was a very nice idea. And basically, what you get from this hardware transactional memory is, first of all, you've got something in the CPU that supports transactions. And it's for any data structure, almost any data structure that you want. It's composable, and I'll get into that later in this lecture. It's fast because it's in hardware. Most of the things that you do in hardware is very, very fast, and so this is also something that is very useful. And you don't get all those deadlocks and stuff like that that we used to have with locks. So basically what you need to do is you need to take your code, put it between the XBegin and XEnd operations. These are CPU operations. And it knows that everything in between should be operated on the transaction memory cache. And it finishes with that. Okay? This is the idea. What are the problems of this implementation? Is basically that this is a very limited data set size. So if your transaction accesses many, many locations in memory, which is, let's say, larger than the cache size, then you basically get, this transaction will never be able to complete. Okay? So this is one disadvantage. The other disadvantage is that if the duration of the transaction, let's say it just accesses a few locations, but the duration is very, very long, then it might be, that thread might be preempted, might be moved to another core, might be all different stuff, all different things may happen. And this needs to be thought about. And so if it's a long transaction, it might not complete. And so this is one of the problems with hardware transaction memory up to today. But we'll get to that. So this was all nice. This was in '93, as I said, right? So, but it's nice to know that Intel, for example, said that the Haswell, this is 2012, they said Haswell will include support for Intel's transactional synchronization extensions, TSX, which is basically what Hurley and Moss did, but in a different manner. One thing to note that before that, there was, I think in 2010, Sun Microsystems also had a prototype for a new ROC processor, it was called, that had some kind of hardware transaction memory. But then Sun Microsystems was bought by Oracle, and this project was abandoned. There's something for AMD. It's called ASF. It's something similar, but it's not actually a transactional memory in this sense, which hasn't gained much of attention. But this thing gained a lot of attention, and everybody was happy when this was out. Everybody was happy, and their implementation is basically based on what we've seen by Hurley and Moss, but just uses the same cache. It doesn't use a different cache for each core, but the same cache. And it's called the best effort hardware transaction memory. Why best effort? Because as we said before, if your transaction is too long in duration or it accesses too many data locations, then it basically cannot support it and it will abort the transaction. And so this is why it's called the best effort one. And this was in June 2013, the first Haswell implementation that they had. About a year later, in August 2014, they announced that there is a bug in their CPUs. And as you probably know, when you've got a bug in hardware, it's not as easy as a bug in software. So basically they said that, I don't know if you can see it, but under a complex set of internal timing conditions and system event, software using the Intel TSX instructions may result in unpredictable system behavior. Basically saying, okay, sometimes it's not atomic, it's not working, basically. But yeah, they found it out after someone who was trying to use that in order to build some system did some tests and just didn't get the correct results, and he couldn't understand why. And then basically they moved that question to Intel, and then they were like, yeah, you're right. When this thing happens, their solution was, yeah, just don't use that for these CPUs. I think that now in the new CPUs, some of them have support to TSX, and the new TSX, not the old one with the bug. But it's very interesting to see that even, like engineers that have a lot of experience with these things, especially, in a company like Intel, still have problems getting stuff right. So don't feel bad if you find it difficult. They find it difficult too. So this is the hardware transactional memory, what we talked about, but was also a suggestion for a software transactional memory implementation. The first one was proposed by Shavit and Twito in 1995. And their idea was, they said that the idea of Hurley and Moss and to do this in hardware is nice, but it's very limited, as we saw. And so let's make a non-blocking implementation that will allow a transaction with a large data set and that may run for a long time. And so, but their problem was that it required that each transaction data set, in their proposal in 95, was that each transaction data set to be static, meaning I will know exactly where, this is my critical region, I will know exactly where it's going to access, what memory location it's going to access. And it also needs to be known before the transaction starts. And so it was nice, but it wasn't very useful. And it didn't gain much attention. But the first time that we saw that there is a library implementation that supports transaction memory. So as we said, it's any data structure that you want. It's potentially very scalable. It's composable, and I'll get to that in a second. And we don't have any lock-based problems. The only thing is that whenever we read something and we want to do a transaction, we need to basically say we want to read it transactionally and write something transactionally and end the transaction. We need to explicitly say it. And so one of the problems that I found that I think that it's typically slower. If you compare it to hardware transaction memory or to specific data structure specific non-blocking algorithm, this is a bit slower. And so we'll look at an example of software transactional memory in a second, but let's talk about transactional memory composability. So the idea is this. Let's assume that we have two data structures that are using transactional memory in order to do their operations. Let's say data structure 1 it has an operation that uses transactional memory, and data structure 2 also has an operation that uses transactional memory. What we want to do is basically compose these into a single operation. Let's say move from one hash table into a tree. Move some data from a hash table into a tree. This can be done in an atomic manner. We just put everything in an atomic block. And so if each one of them uses the atomic, it will just compose itself into a single operation, which is atomic. So it can get, well, this is very easy, and this is very useful, because many times when you look at libraries of stuff that are implemented using, I don't know, either non-blocking or fine-grained locks or stuff like that, it's very, very hard to compose two operations from different data structure into a single atomic operation, unless you use some coarse-grained locking. But other than that, this is very, very useful. So let's look at an example of a software transactional memory that was proposed by Hurley, Luchango, Moyer, and Scherer in 2003. It was called DSTM. And the idea of DSTM is that it's a dynamic-sized transactional memory. So it can support, you don't need to know beforehand what you're going to access, what memory locations you're going to access, and it doesn't need to be in specific memory locations. And they implemented it in both Java and C++. We will look at some of the Java implementation that they had here. But basically, this was in 2003, as I said, just after Intel and everyone announced that they're going to have problems with speeding up the processors and they're going to use multi-cores. Since then, I think like every year you've got like a few hundreds of papers on transactional memory, all sorts of other implementations or improvements and stuff like that, new ideas. But basically, it gained very, very much attraction since 2003. So so first, before we go into the details of how they work, let's just be on the same page and look at the computation model. So we've got threads, right? Threads in our application, they run, and sometimes they want to execute a transaction. And to do that, they need to say, OK, I want to begin a transaction here. And then they can do operations like read transactional from some objects, write transactional to some objects. We write some values. You can also read and write, do regular read and writes, non-transactional read and writes. And at the end of their transaction, what they need to do is execute a commit transaction, invoke the commit transaction, which basically will ensure that everything is committed atomically. So the commit can have two kinds of results. Either successful commit, which means that all the transactions operations take effect atomically, or a failure, and they're all discarded. The previous STM designs, as we talked about, there were only static in memory and static transactions in terms of they need to declare which addresses they're going to access, and they want to avoid that. And so what they did is the following. So before I go to the details of how they implemented, I will show you how to use their transactional memory. So this example is going to be in Java, but if you don't know Java, don't worry about it. I'll just go into the details of like what's important here. So basically, each thread, in addition to its run method, which basically says, OK, I will run, now I can run whatever I want in a separate thread than the main thread, it will also have these operations. Begin transaction to initiate a new transaction, a commit transaction to state that, OK, I finished my transaction, I want all the operations to be executed atomically. Or it can say that, OK, I found something wrong, I want to abort my transaction, so don't do anything. So this was their idea of what a transactional memory thread should look like. And one thing to note is that each thread can run a single transaction at the same time, so at a time. So it cannot just say, OK, I want to begin transaction, then I want to begin another transaction, which is completely different than the previous one, and then begin another one. But you must do a commit before you begin a new transaction. That was their idea. This, as I said, was the first implementation. And so this was their assumption. In addition to the thread, we have the objects that we need to access. So the idea of the object is that each object should have a clone method, a clone function. Basically, take the contents of that object that we want and clone it. We'll later see why it's useful. But the implementers, if you've got a new object that you want, and you need to implement the clone method, it's a basic clone method. Let's say it's a matrix that you probably want to do some deep copy of that matrix. And it's a simple one. You don't need to think about other threads that try to change some stuff. It's basically just a copy as you used to do. So what I suggest is to take each object. In Java, most of the stuff are objects. So take each object and just wrap it with something that's called a TM object. We'll see why it's useful. It's just a container. And this object can be used. We wrap each object with a TM object, and this TM object can be used to do some open. We can use the open method. It has an open method that you also get a mode. And we can either open it for a read mode or a write, and basically read mode. OK? So I explicitly say when I try to access some memory location, I'm going to just read from it, and then I open it for read. Or I'm going to read and write from it, and then I open it for write. We'll see why it's useful. It's basically an optimization. We could have just opened everything for a read-write, but it's basically an optimization to reduce the number of conflicts between transactions. So let's look at an example of using the STM. Okay, so again, we'll look at an example of a counter that starts from 0 and increments by 1, and it does it atomically, and we get the previous value. So this object will be called counter. This thing is basically just says it extends it inherits a TM clonable. It has a clone method. That's basically the first line. It has an inner value that's called counter value. That's the counter that it has. And it has these 3 methods. One is called inc, that increments, doesn't do anything, but just increments the value. There is the value that returns the current value, and the clone method that we need to implement. And this object is shared by multiple threads. How is it done? So when you create stuff in Java, you need to use the new keyword. So we can create a variable called counter with small c. And this basically says, OK, I'm going to create a new counter. And I'm going to I'm going to use the wrapper that's called, this is the TM object on our counter. And let's call it tx counter. So let's say that all the threads have access to this tx counter. When a thread wants to begin a transaction, what it needs to do is call the begin transaction operation. So this is from the thread's point of view, it uses that. It can then it can then open the tx counter in write or read mode. And here we open it in write mode. And then we can call the operations such as inc on that variable. In the end of the execution, we need to call the commit transaction to commit this entire transaction. And this returns true or false, as we said. And why they did that is because sometimes when it returns false, you might want to retry that operation, but sometimes you might want to do something completely different. And this was their idea. So let's look at the implementation itself, because I think this is where the things start to get more trickier. So as we said, everything in this DSTM needs to be wrapped by, all objects needs to be wrapped by the TM object. What is a TM object? A TM object is basically a pointer to something that's called a locator. A locator has 3 fields. The transaction, which is a pointer to the transaction that is running. A new object, which points to the data of that object. Old object that points to another set of data. And we'll understand why they need these 3 fields in a moment. But this is basically what they need. And so we've got here something that has two sets of data, right? So what is the current version? What is the current data set? The current object version is determined by the status of the transaction that most recently opened the object in write mode. So we look at the transaction most recently opened it in write mode, and by looking at its status, we decide where we should look at it, whether we should look at new object or old object. So we distinguish between these 3, whether it's committed, aborted, or active. So whenever we open an object, let's say we want to have a transaction A that opens an object O in write mode, and let B be the transaction that was that most recently opened O in write mode. So we distinguish between the 3 cases of whether B is committed or aborted or active. And let's assume for now that B was committed. So if we look at the TM object of O, it basically looks like this. It points to the B's locator. The transaction points to the transaction B, and basically we're just showing the status here, which is committed. The new object is some data, and all objects is might be some other data. For example, if we have the counter, then this might be the counter that stores 5, and the new object might, and because it's successful, it might be storing 6. Whenever A wants to issue, whenever A opens this object O in write mode, it first creates a new locator, and then sets these pointers. So new object will point to some data that is cloned from the previous new object of B. Old object will point to the new object of B. And the transaction will point to A's transaction, which is basically, we're looking at just the status it's active. And then it will use, whenever it tries to commit, it will use a cas operation in order to replace that location, that TM object from pointing into B's locator to the new locator. So this is the idea if B is committed. And if this cas fails, then A can either restart from the beginning and do the transaction or do some other stuff. What happens if B is aborted? So in case B is aborted, again, and A tries to open the object O for write mode. So again, it creates a new locator. And now it clones the old object just because B was aborted. So its operations did not take effect. So it just needs to take its old object data as its new object and work on that. And the old object will just point, of A's locator, will just point to the old objects of B's locator. And again, it will use the cas operations upon committing. So we've handled the cases where B is both committed and aborted. But what happens if B is an active transaction that is actually running at the moment? So the problem is that both A and B try to access the same data and write to it and at the same time. So this is a problem. And so for this, what they suggested is using something that's called a contention manager that takes two transactions and decides which one should proceed and which one should fail. And if, for example, B needs to abort, then we try to change its status using a cas operation. This was their idea. One of the optimizations that they did is if we just open an object in read mode, not in write mode, just in read mode, then instead of doing this cas operation, which is more expensive than usual read-write and might lead to other failures, we just fetch the current version. Each object has a version. I haven't told you of it for this thing. And it adds the pair O and V, the object, its location, and its version, to something that's called a readers list. So this is a pair transaction readers list. And it just reads from it, and so there's no contention on that. And whenever you commit a transaction, you first validate the transaction, and I'll explain what is validating a transaction. And then you try to change the transaction status from active to committed using cas. Why cas? Why do we need to use cas here? Because it might be that some other thread, if we had a conflict with another thread, it might also want to change our status from, and it decided that we need to abort, it might also try to change our status to aborted, and so it needs to decide to either be committed or aborted, and this is how we gain it. What is a validation? A validation is basically looking at the read set, all the objects that we read, and making sure that the transaction is in a consistent state. Basically, looking at the version of each object that we read and making sure that it hasn't changed. If it has changed, then its object is not pointing to a transaction that is in active mode, then we just need to abort our transaction. Why do we need that? So let's look at this example. So let's assume that we have two objects, O1 and O2, that are initially 0. And then we've got two threads. One is reading O1 into X. That's thread A. It's reading O1 into X. It then writes O2 to O2 X plus 1. And the other thread B reads O2 into Y and writes O1 to O1 to Y plus 1. And so if we look at valid executions, so let's say thread A and then thread B, or thread B and then thread A, then what we get is either that O1 is equal to 2 and O2 is equal to 1, or O1 is equal to 1 and O2 is equal to 2. But if we let them to run concurrently and we won't do the validation, then what we might have is that both of them, O1 and O2, are 1, which is an illegal state. So as we said before, there might be conflicts, and they're detected when we first open an object and then see that this object was modified by another transaction, or when you do the validation step. So for this, what they said, we need a contention manager that takes two transactions, transaction A and transaction B, and decides which one should win. And this should be this policy should be set by anything that you want. Let's say the one that opened more memory locations should be the winner, or the one that ran for a longer time should be the winner. And there are many strategies that you can take here, many policies that you can take here, and basically they left it as something that can be further investigated, and there are many research on this conflict policy. And we'll skip these. Yeah, sorry.
Manager is just like validating the commit or abort.
Yeah, it decides, it looks at these two transactions and decides which one should win and which one should lose. When there is contention. Yeah, this is only invoked when there is contention. And when there's a conflict. And then it says, okay, you need to, you're the loser. I'll try to change your status from active to aborted. And if it's successful, then the other one is aborted. But if it's not, then it means that the other one was probably committed or aborted by some other transaction. And so it needs to look if it was committed, then it needs to maybe proceed. Or just, abort the transaction that it thought it should win. But if it's aborted, then it might just proceed as it is. I will skip that, sorry. There are new software transaction memory implementations. Basically, in the GCC, the compiler, since version 4.7, also has software transaction memory implementations. It's very, very nice. Very, very useful. Later versions also support something that's called a hybrid transactional memory, which it's HYTM, sorry. And so it first tries it in hardware, and if it fails, it goes into software, and make sure that these transactions can execute concurrently and be okay with that. So to summarize, the idea of transaction memory is how to implement non-blocking algorithms, data structures very, very easily. And there are some hardware implementations, but they're pretty limited. There are software implementations, but their performance can be improved. And I haven't mentioned that there are many software transaction memories that are also blocking in their nature. They just do a fine-grained locking, basically, or medium-grained locking techniques. But this is something that is out of your hands. So it ensures that everything is correct, that you won't get any deadlock and stuff like that. And they're useful just because their performance is better than the non-blocking algorithms. Okay, thank you very much, guys.